All right, so we're going to just do a quick example here of how we use the buckling of a column. We're going to look at this element here, which is this rod on this crank arm. And this is a cylinder that, as it pulls in, it pulls this arm back, causes this to rotate, and then unloads these paper rolls. Okay, so this is the cylinder arm in question. I'm moving it on the wrong screen, so we'll just leave that guy up there so you can see him. And this here is question, I believe it's 445, all right, in your book. And what we're going to do is just find what the critical load of this element is going to be, all right? So first we start off with, what we know. So get my pen here. Okay. All right. So this is problem, it would help if I had an ink color that wasn't black. So this is problem 445 in your book. And the question is, what is the critical load of the air cylinder here? So it's this guy. What is the critical? Oh, sorry, not the cylinder. The critical load here on this air cylinder. If the crank arm that rotates it, this guy, you get a different color that has a little bit better contrast here. So if this guy here is 0.3 meters long, and the rod has a maximum extension here of half a meter, and we're told that it's a 25 millimeter diameter steel rod with a yield strength of 400 megapascals. All right. So we have our parameters. L is the rod length, 500 millimeters. Diameter is 25 millimeters. Young's modulus for steel, 207 gigapascals. And the yield strength is 400 megapascals. Okay. So we want to calculate the slenderness ratio that divides the load versus the slenderness ratio graph in the Johnson and Euler regions. So what we need to do is we need to find out where that point is, SRD. And I've added this to the slides. I missed that equation in the lecture, so it's I've put it back on slide 17. It's the equation where we can calculate the slenderness ratio, and that slenderness ratio is pi times the square root of 2e over SYC, and that comes from the fact that the yield strength slenderness ratio is half of the or that point D is half the compressive strength from the Johnson diagram. So let me just bring that over here real quick. I'll show you where that point is here. Okay, so that is that point right here, SY over C. So we can calculate SRD in terms of the compressive yield strength for that material. We'll go ahead and calculate the area. Okay. If I can click off of this. Give me 1 second. second. Sorry about this. Oh boy. All right, there we go. All right, so we have this. And if we calculate the area of the rod, it is pi over 4d squared, which is 490.87 millimeters squared. The moment of inertia for the rod is pi over 64 d to the fourth power. Okay, and that is 1.92 times 10 to the 4 millimeters to the fourth power. The effective length from the boundary condition is just the same as the length from our chart. Okay, and that's 500 millimeters. And then we can calculate the radius of gyration based upon I and A, which is the square root of I over A. And that is 6.25 millimeters. Then we can calculate our slenderness ratio, which is just the effective length over the K. Okay, so in that case it's 500 over 6.25, so that's 80. That's our slenderness ratio. And because our slenderness ratio is 80, and if we work this out for the slenderness ratio at D, we find that this is 101.07. So in this case, we have the case where SR is less than SR at D. And so we need to use the Johnson equation. So we're over here in this region where SR is less than SRD, okay? So where SR here is less than SRD. So we need to use that other expression for the critical load. So the critical load is just A times SY minus 1 over E times SY SR over 2 pi quantity squared. If we do that, we find that the critical load that that component can have to avoid buckling is 134.8 kilonewtons. Okay, so that's how we use this. That's how we determine whether the buckling will occur or not in a quick little example.